Welcome to Study Loop.
So in this problem, we are given a compressed gas that is going through a compression phase from volume V1 to volume V2. So it's getting compressed, and it is getting, then after compression, it is getting cooled down at a constant pressure. This is the pressure at which the gas is getting cooled down. Since the gas is getting cooled down, it is losing its internal energy. So the internal energy given in this problem will be negative as well. For the part A, we need to find the work done by the gas. The pressure is held constant, so the work done by the gas is given by this kind of expression. So this is the general expression for work done in this case, in this situation when the pressure is constant and the work done is only due to change in volume. This is pressure P, constant pressure, times change in volume. Substituting the given values, we know here that it's going to be 1.10 times 10 to the fifth pascals times, and then in brackets we have 1.2 meters cubed minus 1.7 meters cubed. Final dimensions are going to be in joules, and when we evaluate this using a calculator, we obtain negative 9 times 10 to the fourth joules. And this is expected since we know that the work done must be negative when we are investing work, when we are giving energy to the system so that it can get compressed, so that the volume will change. Now for the part B, we need to find the absolute value of the heat flowing in the system during these processes. So from the first law of thermodynamics, we know that the heat will be equal to the total change of internal energy plus the work done from the outside, so the work invested. And here we know that this internal energy, delta U, is going to be negative since the gas was cooled down, and the work done is also going to be negative since the gas was first compressed, the work was invested. So when we substitute the known values, we obtain that it is minus 1.4 times 10 to the fifth joules, and then it will be plus, but again a negative value, 9 times 10 to the fourth joules. Of course, we can put this into a calculator, and we will obtain the final value that it is minus 2.3 times 10 to the fifth joules. So the energy flow will be minus 2.3 times 10 to the fifth power joules. But don't forget that in this part of the problem we need to find the absolute value, so we are not interested if it is plus or minus. This minus says that the heat will go out, but we're not interested in that. We need the absolute value, so it will be absolute value brackets of Q equals absolute value of 2.3 times 10 to the fifth joules, and this is equal to absolute Q is simply 2.3 times 10 to the fifth power joules. And this is the solution for the part B of this problem. And now for the part C. Part C is more of theoretical nature. The question is theoretical, so no, it doesn't matter if the gas is real or ideal. So it does not, sorry for this, it doesn't matter if if the gas is ideal or non-ideal. Why? Well, that's because as you can see, we evaluated the heat flow from the first law of thermodynamics, and the first law of thermodynamics is a fundamental law of physics generally. So it works the same exact way for ideal or non-ideal gases. There are equations that work only for ideal gases, like the law of the ideal gas, for example, is relationship between pressure and the volume with the temperature and the number of moles. This is only for the ideal gases, but the first law of thermodynamics is exactly the same for all types of ideal gases, non-ideal gases, any thermodynamical system in general. So that is why the answer for C is no, it doesn't matter. Because the first law of thermodynamics, which is applied in this solution, can apply to any material, ideal or non-ideal, anywhere. And by this, we have finished the problem completely. I hope this was helpful for you, and I hope to see you in the next lesson. Bye.